Hello student. Today here in this lecture I have discussed about rotational mechanical system. Okay. So mechanical rotational system are similar to translational system except that torque and angular displacement are considered in the place of force and linear displacement. Okay. So moment of inertia of mass, rotational frictional coefficient of dashpot and stiffness constant of the spring are the fundamental elements in a rotational system. Okay. So first we will discuss the first element is rotational spring. Spring is nothing but its spring basically stores energy during the variation of its shape due to elastic deformation. Okay, so the elastic deformation of the body can be represented by a spring constant. Okay, so when a torque T is applied to a spring as shown in figure, okay, so it is twisted by an angle theta. Okay, so the spring will produce an opposing torque that is capital T suffix K, which is proportional to angular displacement. Okay, so that's why here this is, see here this is Tk. This is basically T suffix K. Okay, so this Tk, this opposing torque which is represented by T capital T suffix K, this is proportional to angular displacement. That's why this Tk proportional to theta. Okay, so that's why if we eliminate the proportional sign, then we put a constant. So here we put a constant K. Okay, so Tk equal to K theta. K is nothing but spring constant. Okay, or spring stiffness constant. Okay, so by according to Newton's second law, capital T, that means applied torque, this capital T is equal to Tk. Okay, so that's why applied torque T equal to K theta. Okay, now the second element is rotational damper. Okay, so damping occurs whenever a body moves through a fluid. The damping is represented by a dashpot with a viscous friction coefficient capital B. Okay, so whenever a torque capital T is applied as shown in figure, it is opposed by the damping torque that represent this damping torque capital T suffix B. Okay, so so whenever a torque capital T is applied, it is opposed by the damping torque TB, which is equal to the product of capital B. B is nothing but a viscous friction coefficient and the angular velocity of the dashpot. Okay, so we can write TB equal to B into omega. Omega is angular velocity. Angular velocity is omega equal to d theta dt. Okay, so by according now, TB equal to B into omega. Okay, so according to Newton's second law, the applied torque T equal to damping torque TB, and that's why applied torque T equal to beta into omega, and this is equal to beta into d theta by dt. Omega is angular velocity and theta is the angular displacement. Okay. Now, if both ends of the dash pot are not fixed, as shown in the below figure, then the angular velocity is measured at both ends of the dash pot. Okay, and for this case, the applied torque T equal to this is B. Okay, this is B into theta 1 dot minus theta 2 dot. Theta 1 dot means first derivative. So d theta 1 by dt minus d theta 2 by dt. Okay. Now coming to the third element. Third element is moment of inertia of mass. Okay. So the moment of inertia of the system is assumed. So the moment of inertia of the system is assumed to be concentrated at the center of gravity of the body. Okay. So when a torque T is applied to the body as shown in figure, it produces. So when a torque T is applied to the body as shown in figure, it produces an angular acceleration A. Okay. So the reaction torque capital T suffix J is equal to the product of J, mass of inertia, moment of inertia J, and the angular acceleration. Okay. So that is T suffix J equal to J into A, and this is equal to J into acceleration is double derivative of angular displacement. That's why d2 theta by dt2, and this is equivalent to J into d omega by dt. Okay. So where J is moment of inertia, and this unit, its unit is kg meter square. Theta is the angular displacement, and the unit is radian. Omega equal to omega is first derivative of displacement, that is omega equal to d theta dt. So omega equal to angular velocity, and it is expressed by radian per second, and A is the acceleration, and its unit is radian per second square. Okay, and Tj is the reaction torque, and its unit is Newton meter. Okay, so these three are the basic elements of rotational mechanical system. So now we will see how we will draw a free body diagram of a rotational mechanical system. Okay, the first step is assume the direction of rotation of the mass or direction of the applied torque as positive direction. Okay, and next find all torques acting on the mass. Okay, for example, torque applied, opposing torque due to deflecting in the spring, opposing torque due to angular velocity in the dash pot, and opposing torque due to angular acceleration in the mass. Okay, and third step is using Newton's law of motion, express all the torques in terms of angular velocity, angular acceleration, and angular displacement of inertia element. Okay, so see here the free body diagram of a, here I have given one rotational mechanical system, and I also derive I also draw the free body diagram of this rotational mechanical system. So see here Tk is the force which is applied by the spring. Okay, and this is Tj, this Tj equal to J into d2 theta by dt2, and Tb equal to B into d theta, B into d theta by dt. Okay, so from the Newton's second law, we can write applied torque T equal to Tk plus Tj plus Tb. Okay, so if we taking Laplace transform, if we taking a Laplace transform of both side, after putting Tk equal to k theta, Tj equal to J into d2 theta by dt2, and Tb equal to B d theta dt. Okay, then if we are doing Laplace transform on both side of this equation, then we will find the transfer function of this mechanical system. So what is the transfer function of this mechanical, what will be the transfer function of this mechanical system? So see, this is the transfer function of this rotational mechanical system. Okay, so now you people understand how we will draw a free body diagram and derive the transfer function of these two type of mechanical system. One is translational mechanical system, second one is rotational mechanical system. Okay, so here I have also given how we will calculate the transfer function of this rotational mechanical system. So now see this table. Actually this table represent mathematical models of mechanical rotational elements. Okay, so first one is mass, second one is dashpot. Okay, and spring, third one is spring, then dashpot with both and free, spring with both and free. So this table represent the mathematical model of each and every element of mechanical rotational system. Okay, and this table represent mathematical model of mechanical translational elements. Okay, so first one is mass, second one is spring. So first case 1 and fixed dashpot, third one is dashpot, and fourth one is spring. And here spring style in both ends are not fixed. Okay, and last one is dashpot. This so in the case of dashpot, there are here see the both end are not fixed. Okay, so this table represent the mathematical model of mechanical translation, each and every element of mechanical translational system. So thank you student. Today I will stop here.